How is everybody? Good. What did you guys think of conference? It was so good. So good. What was that? Everybody got in trouble. We were all chastised. If the Spirit didn't do it, they did it for you, for the Spirit. So, Elder Bednar is hilarious. Why do you say that? Oh, you talked about how, because of old food storage, they decided not to open because they didn't want to start another worldwide pandemic. I missed a few talks because I was helping a neighbor, and so I listened to them this morning on the way to work. And one was Elder Matthew Holland's talk, and I thought he had a good one about passing the kidney stone, and something about by great things are the small and simple means are great things about to pass. And he said, nothing so great has come by something so small that had to pass or something. So, hey, was it this class that I talked about my patriarch speaking in gospel? Yeah, when he was a deacon. In 1983, Elder Matthew Holland also spoke in General Conference, and he was, 17. So, yeah, he may hold the record for the longest distance time between talks in General Conference. I don't know. So, yeah. I only learned that after I talked about it this week. Who'd like to start us off with a prayer? Thank you. Amen. Thank you. One thing that popped out to me, maybe just because I'm a professor, but Elder Bednar talked about his job as being a professor. He said that his job was to do two things. Do you guys remember what they were? It was like the first talk. So you forgot it all, huh? It was, his goal was to help students learn how to learn and to evaluate them on their learning. So, and he talked about tests, like grading exams and giving students feedback and how it's tough. And one of the reasons I have you guys read the section is to help improve give you practice in learning how to learn. And when you think about it, there actually really is no such thing as teaching. There's only supporting your learning. Like, no matter what the teacher does, like the learning that happens is completely up to you. There's certainly some interaction that happens, right? Like there's I can give you better opportunities to, but it's really supporting the connections you are making with the material. People often talk about that people learn differently. Actually, everyone learns exactly the same way. They learn by taking what they're experiencing and connecting it to things they already know. Everyone learns that exact same way. You know different things, right? So you'll be able to make different connections, but the basic process is that same thing. Anyway, so one reason I throw that out is take seriously your learning, because it's a very active process for you to be making sense of things and making those connections. And sitting and just watching me do things doesn't usually help very much. All right. Any comments about devotional today? Oh, yeah. That was the comment. Yes? Okay, so that comment, say that again, that the atonement was, the atonement makes it possible for angels to descend and minister. What a concept. So Very cool. Any other comments about the devotional? Ah, she mentioned orthogonality. That's right. So very good. Yeah, we haven't spent a lot of time talking about orthogonality. It'll bump up later in full force. My son is in a programming class and learning how to design code, and they also use the idea of orthogonality in there. In that, when you change one thing in the program over here, you shouldn't have to go and have to change something over here. So you want them unrelated in a sense, and that's orthogonal. They're unrelated. Okay, very nice. Her office, Candace Barrett's office, was just above us over here, but now the stats department's moved. They're over in the Westview building. Okay, we better talk about homework. So no written homework today, but we are prepping. We are starting a new section on Thursday. So read 3.5 up to the section bases. You don't need to read that section, just up to that heading bases. Watch the 3.5a video. I'll make it after class today. It's not up yet. And do the online homework for 3.5a. We're going to spend 3 days on this section, or 2.5 days on this section. There's quite a few ideas in here. And then study for the exam. The exam starts tomorrow. It goes until Friday night at 11:59 p.m. We have put a 4-hour time limit on it, just to keep information from flowing between students. So I'll send an email out with all the details of the exam. It'll be on Gradescope. It is not proctored, but it is not open book, open note, open internet, no calculators, etc. So you need to be on your honor when you take it. If I would have known that beforehand, I would have encouraged us to write a different kind of test, but yes. No, I'm going to film you taking the test. Yep. So you don't have to dress up for it. So, okay. And then, yeah, study for the exam. Other questions about the exam? I will send out an email with all the details, but if you've got questions, I'm happy to answer. I think so. We shoot for that. So, yep. So the question was: are the questions evenly divided across sections? And yeah, there'll be at least one from every section. But yeah. Yep. Yeah. Expect there to be a proof. So, yay! That was the comment. Was yay. And there was much rejoicing. Okay. Other comments or questions? Yes. Yeah, same format as the practice exams. So multiple choice. I don't know if there's actually a short answer. There's free response, and since it's on Gradescope, you can just write out your response, take a picture of it, and upload the picture for your answer on the free response. The multiple choice, I think it's already set up in the system where you just click on the multiple choice. So, okay, other questions? Okay. So the idea of today is I'm happy to answer questions. Any questions you have about any of the material, I have the 2 exams here. If you have questions on how to do problems from the practice exams. I also wrote some problems, and some of you I see are already working on these. So these questions are on Learning Suite. So especially for those of you that are online, because these are going to, you might, if you want to keep working on these, pull out your camera and take a picture. Because as I start working on the board, we're going to want to have that there, or have your neighbor take a picture, and you can do that. Take a selfie with that in the background, post it on Instagram and stuff. These are online too. It's on the Learning Suite page, the same place that the practice exams are. So you can go there also. Okay. So let me just open it up. What questions do you guys have? Yes. What are the double lines next to U on number 4? Where's my, there. So, anyone want to shout out what these are or take a guess? It's the magnitude. They're kind of like absolute values. Absolute values tell you the distance from 0. This is the length. This is, we call it the norm. So this is the length of vector U. So if U is, it's the square root of U dot U, or if U is U1, U2, U3, UN, then this is going to be U1 squared plus U2 squared plus U3 squared, UN squared, square root. So you should be able to see the Pythagorean theorem in there, right, in 2 dimensions. You've got a vector that's 3, whatever, 1, 2, 3, 4, 5, 6, 7. So if U was the vector 3, 7, then the length of that, you can use the Pythagorean theorem to figure out 3 squared plus 7 squared, take the square root. So that's where that comes from. Nice, good question. Other questions about anything? Yes?
For the second problem, it's asking if U, V, and W are linearly independent or dependent. Can you remind me how to set that up? Like, would you put it in a matrix and then have it time for electron form? Is that how you would do it?
So the question was, question number 2 asks if U, V, and W are linearly independent or dependent. Have you done problem 1?
Yes.
Okay, so problem 1 asks if the matrix with, okay, well, let's address your problem 2. So if they asked, hey, are these 3 vectors linearly independent or linearly dependent? Someone tell me what these are. 1. Okay, so you can put them in a matrix and start row reducing. How's that going to tell you if they are independent or dependent? Yes. Okay, if there's a free variable, they're dependent. So if each of these is a pivot column, they are dependent. When you get 3 pivot positions, they're independent. Okay? So, but if I get a free variable, then I know, then that means that variable is just a combination of these other 2 vectors. Sorry, that one vector is a combination of these other 2 vectors. So they would be linearly dependent. You're welcome. So you actually found, but on problem 1, you found an inverse, right? You put these together and found the inverse of this matrix. If that inverse matrix exists, what do we know? That they're linearly independent. Because you were able to row reduce it to get it to make it look like the identity matrix, right? Yeah. So if you know that the columns or the rows make up an invertible matrix, then you know they all have to be independent. Yes? How do you know if it's invertible? That's transpose. Yeah, so don't mix up the idea of invertible and transpose. Okay? So any matrix has a transpose. You can take the transpose and rewrite it. So the transpose this would be the transpose. Okay, so I took the first row, wrote it as the first column, took the second row, wrote it as the second column, took the third row, wrote it as the third column. Okay, and I reflected it along that diagonal line. So this is the transpose, but it's not the inverse. If the transpose is the inverse, then you have something very interesting going on. I don't know if we'll get to that in this class, but so how would we figure out what the inverse is to this? Yes. That's right. We have a process for this where we're going to augment it with the identity. And then we're going to row reduce this side. And if we can get this side to be the identity matrix, if it can row reduce to that, if it's row equivalent to that, then what we end up with on this side is the inverse to this matrix. Okay. Should we do that? Okay. Okay, how about everyone work on that problem, okay, for a couple minutes. Find the inverse of this matrix. If you've already done it, work on some other problems that are somewhere right there.
So when you're checking for dependence for your augmented,
you've already done this, you can help me correct my mistakes up here. So I'm trying to do it. Okay. Thanks. Because I have a minus 1 and 2. Wait, someone already did this? No. Thanks. So, what did we just do? Magic? Waste 5 minutes of your life? No. So, what's this side is the inverse matrix of that. Okay? So we found the inverse matrix. It exists because we were able to reduce this left side to the identity matrix. So once we knew that there were, once I actually got to here, I knew that it was invertible. How did I know once I got to here that this was an invertible matrix? There's no free variables. I have a square matrix with no free variables, but I know I've got these 3 pivot positions. I know I can continue row reducing, so I'd have 1, 1, 1 and make those others 0. So we're good. Like once I get to here, like, because by the invertible matrix theorem, or what the book calls the fundamental theorem of invertible matrices, there's a whole bunch of things that are equivalent to being an invertible matrix. One of them is the columns are linearly independent, or the rows are linearly independent. Or it's really equivalent to the identity matrix. All of those. Okay, yes? Okay, so the question is about what do you have to do to justify that there is no solution? Let me throw this up. Okay, so first, I'm going to build up to that question. So first, is this system consistent or inconsistent? Last class, someone asked what the meaning was, so I thought I'd better hit it on this class too. So what does it mean to be consistent? A solution exists. Whether it's 1 or infinite, a solution exists. Inconsistent? No solution exists. Okay? Okay, how many solutions are there in this case? Is it infinite or finite? Okay, thumbs up if it's finite, thumbs down if it's infinite. Okay, just in front of your chest. And thumbs sideways if you don't know. Thumbs up is finite, thumbs down, infinite, and thumbs sideways if you don't know. Some people are choosing not to do this, so you should, we're about half and half. Maybe a few more thumbs down. So, so some of you are thinking, oh, there's a row of zeros on the bottom, it must be infinite. Okay, a row of zeros does not mean that there's infinite solutions, necessarily. So there's not infinite. If you have a square matrix and there's rows of zeros, then yes, there are infinite. But here we only have two vectors, and there is a solution. We don't have any free variables here. Each of these we have a pivot position in each of these columns. There's no free variables. Okay, so this situation is a situation where I have two vectors in R3. Okay, I've got my two vectors, R3, think of this room. I've got my two vectors here, and that point that I'm trying to get to is in the plane spanned by those two vectors. And there's exactly one way, one combination of these vectors to get to that one point. Okay, there is exactly one solution. Okay. So yeah, just because you get a row of zeros at the bottom doesn't mean that you have infinitely many solutions or that you have a free variable. If you have a square coefficient matrix, then it is true, but not always true. Okay, so what about this matrix now? This augmented system, how many solutions does this have? 0. So there are no solutions. Like that, those two vectors, they span a plane. These two vectors, they do span a plane, and I can get to any point in that plane by taking some combination of these vectors. But that's a point that's not in that plane. 2, 3, negative 2. I'm sorry, 2, 3, 2. It's not in there. So no matter what I do, I cannot get to that point. And so to justify, you can just say, you can just circle this and they say there is no solution. So yeah, you don't, like it's, we've done enough of these that's sufficient on the exam. So, okay. Or you can say, well, this is equivalent to 0 equals 2, which isn't true, so there is no solution. Okay, other questions? Oh, well, here, let's go here.
So if that was a 3x3 matrix instead of 2x3, then if there is a row of zeros at the bottom, it would have infinite solutions.
Right. If you have 3 by 3 and you've got a row of zeros, yeah, if you row reduce and you get this, then there is a free variable here, okay? Because we've only got these two pivot positions. So, so we do have a free variable. Yep. You're welcome. Okay. Good job asking questions, by the way. I remember my older brother, he was about 3 years older than me, and he was really good at mathematics. Probably much better than me, actually. He went on to become a rich doctor, so it's better at me in lots of things. But he doesn't get to have as much fun. He's a radiologist, so he just has to sit in front of a computer all day. At least I get to take time out of sitting in front of my computer to come play with you guys. But he was always asking my dad questions. My dad was a teacher, and then he got into school administration. He was a math teacher. I'm the closest one of his kids to follow in his footsteps. And I remember asking him, I said, Dad, how can Daniel be so good at math? He's always asking you questions. I thought that was a reasonable question to ask. He said, he's good at math because he's asking questions. Like he wants to understand. He doesn't understand something, he's asked questions. He's trying to figure it out. And so it makes sense to him. So, let ask questions. Okay, back in the back, you had a question. I forgot your name. Ryan. That's right. Because that can be like a z equals 0 or x equals 0. So that's, yeah, that's okay. But here you have 0 x's plus 0 y's plus 0 z's equal 0. That's all right. But 0 x's plus 0 x's plus 0 y's equals 2. That's impossible. So yeah, to make sense of that, it's easiest. It might be easiest to rewrite it as a system of equations, so you can see it. So should we do that? 1x plus 2y equals 2. 0 x's plus 1y equals 3. 0 x's plus 0 y's equals 2. No matter what you throw in there, no matter what values of x and y you have, this side cannot equal 2. So it's impossible. Okay, other questions? Yes? You will need to have that memorized. So, yep. So the question was, should you memorize the projection formula? Absolutely. So the projection of u onto v, it's actually not hard to memorize. Okay. So first, a projection is just a scaled version of the vector you're projecting on. If this is v and this is u, what is the projection? The projection is this red arrow. Right? So it's just a scale, the projection is a scaled version of v. So you better have v as your as the vector here. The dot product is a constant. The dot product here is a constant. This is, and a constant divided by a constant is just a constant. You're just going to have a constant times that vector. So if you're projecting onto v, then you better just be scaling v, right? And then everything else. Did I make a mistake here? See, it's so easy to memorize. Even I can't do it. So, yeah. So, and all these other ones are the same as this, except for the dot product. You have one of one and one of the other in the numerator. So, yeah. Did I get that right? There. See, it's projection onto z of u. Yeah, so they're all z's. They're all that lower one. They're all this one, except for that dot product in the numerator. So now you can see the answers to all of these that we're doing up here. They're just further down on this same file. Okay. All right. Other questions? Yes.
On number 3, pretty much we just solve the equation and then we put those the x, y, and z in front of those coordinates for those vectors.
Yes. So the question is, on number 3, we solve the equation and then we put whatever our solution is as the coefficients of u, v, and w. Right? Yes. What is the easiest way to do this problem? What's the easiest way to do 3? So someone said it over here. Yeah. You've already done all the work for in number 1. You found the inverse of A. So let's use that. So, so the question is, can we find combinations of u, v, and w? And u, v, and w, it's the same matrix we were working with before to find the inverse. 2, 1, 2, and 2, 1, 3. So is there some combination of these vectors that can equal this? That's what we're looking for. Well, we can rewrite that as ax equals z, where A is this matrix, this coefficient matrix. X, it will be the combinations of those. X, this is an x vector, right? This is a z vector. So this x is like x, y, and z. Let me rewrite it just to make sure we're all on the same page. 0, 1, 0, 2, 2, 1, 2 times x, y, z. Or we could rewrite this as x1, x2, x3, 2, 1, 3. Okay, if we want to figure out what x, y, and z is, because when we, this multiplication, we could rewrite as that's x times this first column plus y times this second column plus z z times this last column. And when does that equal 2, 1, and 3? Okay. Oh, I'm using z in 2 different ways here, huh? Oh, man. That's horrible. Okay. We'll do x1, x2, x3, x1, x2, x3. Because z is supposed to be this vector, and then I was also using z as an unknown right here. So, and x is yeah, never mind. Okay. So these are all equivalent. Okay. So if A is this coefficient matrix, then and Z is that, then all of those are equivalent. So if we already know the inverse of A, then what's the easiest way to find x1, x2, and x3? Yeah, we're going to multiply both sides by A inverse. So these will multiply together to be the identity matrix. The identity matrix times the vector will just be the vector. So I get A inverse Z. So you've already done all the hard work. You don't even have to row reduce this. You just take this and multiply it by 2, 1, 3. Should we do it? I guess we don't. Do you guys want to do it? Okay. So a minus 2 plus 1 plus 3 halves. So a minus 2 plus 1 plus 3 halves. Then a minus 4 plus 1 plus 9 halves. A minus 4 plus 1 plus 9 halves. And 4 minus 1 minus 3. I can do that one in my head. Okay. What do we get up here? A half. What do we get right here? That's 11 halves minus 8 halves. So that gives me 3 halves. 0. I've already done this problem, so I already know what it is too. So I should be embarrassed that I couldn't just write them down right there. But, so 1 half, 3 halves, 0. So what combination do I take? What's the linear combination of these that will equal 2, 1, 3? 1 half of 1, 2, 0 plus 3 halves of 1, 0, 2 plus 0, 2, 1, 2s equals 2, 1, 3. So that's a linear combination. I could also write it as like 1 half u plus 3 halves v plus 0 w equals z. So, okay. I know people are yawning. I know it's so boring. Yes? Could I do the setup for number 7? Yes, okay, so everyone spend a minute trying to think about how you would do number 7. You can start working on it. Think about how you would, at least, yeah, you can at least get it set up. Sorry, what was that? It's similar, except you don't have the same set of vectors. You have UV and Z instead of UV. Yeah. It is the same general setup. So U was 102, V was 120. Dang. One, 2, 0. No, 102. Okay. 102. No, 2 and 3. Okay. I'm doing the homogeneous equation. So homogeneous means I want to know when it equals this 0, the 0 vector. Okay. So a homogeneous system, you're always equaling 0 on the right-hand side. Yes? Bottom right. So, so that's for number 1 and 2, that is right. But we're done doing number 7. Right? Where's my? And number 7 says UV and Z. So yeah. So and W and Z, there's only one difference. It is that difference you pointed out. So this was 2, now it's 3. It's the only thing we've changed. Okay. Have you guys started working on this? Doing this? Spend a little bit more time. Go ahead. So the question is, find the solution to the homogeneous equation where we have that system. So the homogeneous equation is when we have a system where the right side, like the constants, are all zeros. So AX equals 0. This is a very common way to write the homogeneous system. So that's different than AX equals B, where B is not, or at least one of the values here is not 0. So this is called the homogeneous system. And the homogeneous system, there's always at least one solution. So it's a system where there's always at least one. You have the trivial solution where all of the x's are 0. So if we came over here, and this right-hand side, we really just wanted it to equal 0. Well, that's easy. I can have 0 of these plus 0 of these plus 0 of those. I can always do that. If there's a solution where these weights, these constants are not all 0, then that means there's some dependency going on here. So. Yeah, if the only solution to that homogeneous equation means that x equals 0, y equals 0, z has to equal 0. If the only system there, if the only solution is that trivial one, that 0, 0, 0, 1, then they're independent. Yep. Yes, Ian? Aha, yeah. So if you're clever, I wouldn't have picked this up, but if you're clever, we actually already have a hint about what's going to happen with that problem over there. That we already know that half of x and 3/2 of y equals z. I don't need this. I don't need this vector at all. So I already know half of this plus 3/2 of this added together will get me z. So I already know that this this is going to have infinite solutions over here. So, if you made that connection. So, good job. I'm impressed. I wouldn't have done that when I was in your shoes. So, I did do it now. I wrote about that in the solutions, so I've learned something. Like, now's a good time for you to realize how much you've learned in this class, right? If I'd handed out the very first day of class these practice exams, like, you wouldn't even know what the questions were asking. And now, you know what, at least one, I'm just kidding. No, you do, you know a lot of these things now. Okay, so we can start row reducing the same way we were doing this. So if I take a minus 2 of this row, add it to this row, I get 0, a minus 2, a minus 3, 0, 0, 2, 3. Already we can see we've got a problem. It's not a problem. We get infinite solutions. Because we're going to have, I'm not going to have a pivot column over here. The reason we have infinite solutions isn't because they're all zeros on the bottom. The reason we're going to have infinite solutions is because I have a free variable. So then I get 1, 1, 2, 0, 0. I could divide by 9 minus 2 here to get 1, 3 halves, 0, and then when I add these two when I add this second row to the third row, I get 0. Okay, and then I can keep on going. I can use this to get that, to make that 0. So I take a minus 1 of this row and add it up. I get this will be 0. A minus 3 halves plus 2 is a half. And lo and behold, we get the 1/2 and the 3 halves again. It's no surprise that 1/2 and the 3 halves. Because when I start writing out the solutions, I have infinitely many. Let's write out exactly what those solutions are. I can take my z's to this side, write it out as a system. It's always easier for me. 0x plus y plus 3 halves z, and then here I just get z equals z. Just write that down. And so let me take all the z's over to the right-hand side. We're going to have x equals a negative 1/2 z, y equals a negative 3 halves z, and z equals z. So the solution, x bar, like the x, y, and z, is going to be any combination where I have a minus 1/2, a minus 3 halves, 1 times whatever my z variable is, or times t, right? In the solution I did z. I should have changed it to t. Okay. And again, if we were really clever, we could have figured that out all the way over from here, because any value I have for this one, I can cancel it out. Every time I have one of these, I can cancel it out by taking a half of this one and 3 halves of this one. And so that's what this says. For any t I can cancel it out with the minus 1/2 of dx of this column. So any value I have for this one, if I take a minus 1/2 times that value and a minus 3 halves times that value, those will all add up to be 0. So, okay, if that helps. Well, sadly, our time is done. So, study hard. I'll send out an email about the exam with all the details, and you guys will do fantastic. So, have a great day.